Have you ever been tired? Imagine that you're flying a plane. It would be bad if you fell asleep flying. Wouldn't it be great to have a robot that could tell you when you need to take a nap? Now introducing our senior design project. The system is designed to detect the eye movements, saccades, and non-movements, fixations, to determine if a person is in a state of cognitive dissociation. This provides an early detection system in high-stakes environments, such as flying a plane.
Eyes and their movements, both typical and atypical, tell us a lot about the cognitive state of a person. In order to track these movements and utilize the information from these movements, we need to be able to have a lens that zooms in on the eyes to record the saccades and fixations, image sensors that relay the data, a development board to store and analyze the data, and a display to show the output. Let's say you're trying to see something. Normally, your human eyes just pick up when light hits the corneas. But let's say that you want to be able to focus light wherever, not just on your eyes. Using a novel, new technology called a lens, you can focus light wherever. We can use this to look at the eyes and make sure we're zoomed in enough to pick up when they move. Now, to figure out how far we need to zoom in, we need to do one thing we all hate: math. Anyways, it turns out that if we have a lens with a 3 times zoom, we can see the eyes move. In order to relay the visual data from the optical lens to the Ultra 96 development board, we used KiCad to design and edit a printed circuit board specifically for that function. The PCB, also known as our bezel board, is a multi-sensor board that includes 2 image sensors. The lenses sit on the top right and top left of the bezel board, directly on top of these 2 image sensors. The blue traces relay all of the visual data up to the top of the board and through a ribbon of data lines straight to the development board. The PCB handles a lot, but its function is simple: translate optical data from the lens into electrical signals that can be stored on the development board for machine learning analysis and display.
To capture video data, we need an image sensor. Luckily, you can buy one, and previous teams have designed a board that connects the chosen image sensor to the rest of the Ultra 96. But the image sensor needs to know what to transmit, and the Ultra 96 needs to know what it's receiving. To do this, they both need to be initialized by driver scripts. We chose to write the image sensor driver in Python, where we can change the resolution and frame rate with these different groups of values seen here. And we chose to write the receiver driver in Bash. The image sensor and receiver were monitored by yet more scripts to make sure the data was moving through the system correctly.
To verify the video and access all individual video frames, we needed the ability to display to a screen. To accomplish this in real time, we used VLC Media Engine and code that will be able to display directly from the output of the video pipeline to the display of the development board. Using this system, a machine learning model will be integrated to detect the eyes of the subject. This model will accurately predict the status of the pilot in real time and provide warning if needed. The system that we are developing provides a real-time, end-to-end detection system for cognitive dissociation. Thanks to it, we will not have to worry about our pilot falling asleep at the helm again, because the system that we've developed will be able to detect when he is sleepy based on the motion of his eyes.